I want to stop this lecture with a kind of harder, more advanced problem, and so maybe you should view this as bonus or, hard homework, hard test level problem on how to do cylindrical coordinates. So my region here is within x squared plus y squared equals 1. That's a cylinder. That's the cylinder R equals 1. Above z equals 0, that's the xy plane. And below the cone, z squared equals 4x squared plus 4y squared. I tell you it's a cone, but you can also see that it's z squared equals 4r squared. And so if z squared equals 4r squared, taking square roots on either side, you have either z equals 4r or z equals minus 4r. And that means our picture in the ZR plane has these two lines with slope 4 and slope minus 4. And those, when you spin them around, give you a cone. When you rotate them, as I mentioned in the first part of the lecture. So that's why this is a cone. I've just changed the slope of the cone to be 4. And so the region that we're integrating in to find, that we're integrating over, looks something like this. I've got this cone. And I also have the z equals 0 xy plane. And I've got the cylinder, x squared plus y squared equals 1. Now, that's r equals 1. So I can also graph that over here. In the ZR plane. ZR, so you can see it runs up an intersection. There's like a point where it intersects. And so at height z equals 4, we're going to run into this circle. So z equals 4 up at this intersection. And so there's a cylinder, and it's outside of the cone below that point, and then it's inside of the cone kind of above that point. Now we care about the region within the cylinder and below the cone. So the region we actually care about is kind of this shape. And I've highlighted, but it's actually also wrapping around in front of the cone, right? So it's like I've taken the cylinder and I've subtracted out this cone inside of the cylinder. So you could actually find the volume of this region, if that were the problem, by doing a difference of the cone volume and the cylinder volume, subtracting the two. We want to integrate, so we need to give some bounds. So let's do that. The other thing I should maybe draw is the xy plane. You can already see in the xy plane in this picture. So in there, we have a circle, and that's going to be our polar coordinate circle. So this is the plane z equals 0. Here's my y-axis. Here's my x-axis. And this is our base for our region of integration. And so I'd like to kind of go between all these different pictures. So over that base looks like this kind of horizontal line in the ZR plane, because it's the base of the region. And I only want to go up. So in this picture, so you should imagine, okay, I can parameterize a disk totally fine. If I'm at a given theta, if I'm at a given r point here, as I go in between my minimum and maximum values for r, I'm going to pick that point here And in order to integrate to find this region, I need to go above the z equals 0 plane and up to this z equals 4r. And so this should be giving you your polar coordinate, the cylindrical coordinate setup. So let's just write them down. Theta should go from 0 to 2 pi. R should go from 0 to, what is that circle? That is the circle x squared plus y squared equals 1. Let's label that somewhere. So that's also r equals 1. So r goes from 0 to 1. And then z goes from 0 to 4r. And that's it. I guess, I need to plug in my x's. So r squared cosine squared theta, r dz, dr, d theta. And at this point, you're in good shape to do the rest of the integral. Because this is a little bit of bonus content, I'm just going to actually evaluate it for you so you can follow along. So let's give myself a little duplicate of that. Okay, looks good. So to integrate with respect to z, there's no z's. I just get a z, and I plug in 4r and 0. So that gives me a 4r. So my new integral is theta equals 0 to 2 pi. R equals 0 to, 1. Let's correct that. Ooh, there we go. There we go. 1. Okay, looks good. 1. Inside I'm going to get r cubed, but then this other 4r. So that's 4r to the 4th cosine squared theta dr d theta. Integrating r is going to be pretty easy. I just get r to the 5th divided by 5. So 4/5 r to the 5th, 0 to 1, cosine squared theta, d theta. To do cosine squared theta, I'm going to have to do a half angle formula. So let's see, 4/5 r to the 5th evaluates to be 4/5. And then I'm left with 0 to 2 pi. Cosine squared theta is the same as 1/2 1 plus cosine 2 theta d theta. And I get 4/5 times a half gives me 2/5. And then I'm integrating 1 to get theta. And cosine has to come from a sine 2 theta. And chain rule tells me I'll get a 2, so I have to multiply by a half to cancel. I'm evaluating theta from 0 to 2 pi. So my final answer for the volume of this region looks like 2/5 times 2 pi plus sine of 4 pi, that's 0. 1/2, it doesn't matter. Minus 2/5, 0 plus 1/2 sine of 0, which is also 0. So I just get 4 pi over 5, and I'm done. Okay, and now, since I'm uploading a new version of this lecture anyway, I'm going to make a correction to an error that was pointed out in the problem. So I'm going to scroll up. Up here, I made a mistake. I'm going to make my corrections in yellow. So z should be 2r and minus 2r in this picture. So these two numbers should be updated. So this is 2r minus 2r. And so also right here, this should be a 2 for my z-intercept in this picture. Continuing on down the page. Those 4 r's become 2 r's in these bounds. So this should be a 2r. And so this one should too. And then that's going to change just this coefficient. Should be a 2 instead of a 4. And so here's a 4, that should be a 2. Here's a 4, that should be a 2. And so I think this 2 now, I divided by 2, this should be a 1. This should be a 1. And this should be a 1. Which means that my final answer should be 2 pi over 5. And that's my correction to the lecture.